Nancy, you can admit the folks.
Yep.
Perfect. All right. Good afternoon and welcome from Aaron Smith and Nancy Bakeman with the Energy and Environmental Building Alliance and our podcast webinar series. We're really excited to have Pat and Travis here from Brown Newtone today. Had a chance to see some of their new products done at the Southeast Building Conference Show and out at PCBC in California, and really excited about what they're doing. But they're going to focus a lot on building science and the education of ventilation's role in high-performing healthy homes. So with that, we have a Q&A section. Please put your questions there. We'll present those to our speakers throughout today's conversation. And with that, Travis, I'll turn it over to you.
All right, sounds good. I'll let Pat introduce himself and then jump in.
Okay. Yeah. Hello, everyone. Excuse me. Yeah. Hello. Thanks for hanging with us today. My name's Pat Nielsen, Brown Newtone, and I'll kind of be handling the first half of the presentation today. And then Travis, who is our group product manager for Fresh Air Systems, our HRVs and ERVs and so on, will get into a little more detail about those types of systems. So what we want to focus on today, again, is not just, we obviously want to build energy efficient homes. That's what EBA is all about, but make sure we're not forgetting about health and indoor air quality as well. So we'll talk about how today's homes, can be problematic. And then we'll have a lot of focus, again, Travis takes over in the second half about how ERVs work, why they're efficient, how to choose the right one. There's a few different ways to install them. He'll cover those options. And then at the end, Travis will also touch on some new things going on with air quality monitoring and automation. How can we make ventilation not only efficient and healthy, but smart as well? So today's homes are tighter than ever. Kind of preaching to the choir here to EBA builders. You know better than I all the different ways, spray foam insulation and so on. It's great for making, saving the planet, making our homes easier to heat and cool. But again, build tight and ventilate right. You may have heard of that. Build as tight as you want. That's a great thing. But let's talk about making sure we ventilate right and have good indoor quality as well. So the pandemic, which hopefully is in our rearview mirror now, it really is going to have some lasting impacts. First of all, even outside of the pandemic, 1 in 5 households have someone with some sort of respiratory problems. And unfortunately, a lot of times it's our children and the elderly that it hits the hardest. So, and COVID really raised awareness of indoor air quality. We're seeing that in the growth of IAQ monitors. You go online and there's a bunch of these different $200 monitors. Their sales are really taking off. So that, that really tells you that prospective homeowners are really worried about indoor air quality in the home they're going to purchase. During COVID, I think it was 2021, ASHRAE and the CDC both published guidelines, how to improve ventilation. You have one person sick in the house, how do you prevent it from spreading? So, again, it really got a lot of social media and, public awareness out there. And we're seeing a lot of builders, probably many of you on the call here today, focusing their messaging a little more on healthiness of their homes. Not just we're going to build an efficient home, beautiful home, we're going to build you a healthy home as well. We'll give you that peace of mind that, home that your family's going to be living in is going to be healthy. So again, more airtight envelopes is making fresh air and indoor air quality a little more challenging, right? You all know spray foam insulation is becoming much more popular. Air sealing technologies like Aero Barrier, just all sorts of better products. We've seen ACH 50 blower door scores come down from 12 plus in the 70s to today we're low single digits. Again, many of you on the call, EBA members, you're probably well below 3 on average. And obviously people don't open windows less often. 30, 40 years ago, that was the way a lot of people monitored their their temperature and comfort. Now just about everyone has central air, so windows are closed all the time. So you're not getting that nice natural infiltration. What pollutants are we concerned about, in terms of indoor air quality and health? Here are a few of the key ones. One is particulates. And when you talk particulates, the one you'll hear about most is probably PM 2.5. If you don't know, that stands for particulate matter 2.5 microns and less. So the reason is, there's also PM1, PM10, and so on. 2.5 micron and less is a size that can go right through our noses, right through our lungs, and into our bloodstream. So very concerning. And there's a lot of different sources of it around the house. So we'll talk about that. One key source in particular is cooking. Whether you cook with electric or gas, you're going to have PM 2.5 coming off whatever you're cooking. But especially if you're cooking with gas, now you're talking about carbon monoxide, carbon dioxide, nitrogen dioxide, PM 2.5, all these other nasty things. So good kitchen ventilation and overall home ventilation, especially important if you do a lot of cooking, and especially with gas. Gases and VOCs, things like formaldehyde coming off carpets. A lot of people like that new home smell, but a lot of that smell they like is things that are not good for them. Paints, off-gassing, VOCs, and so on. Excess moisture, I think a lot of people don't think of that as a pollutant, but obviously it makes us uncomfortable. It can cause mold and mildew issues. And another key piece of that is a lot of the bacteria and fungi and so on that we're concerned about, they really thrive in high moisture environments. You get up above, 50, 60 RH, and these things, that's where they love to reproduce and multiply. So we really want to manage our RH in our homes. Odors is an obvious one to worry about. And one I don't have on this list, carbon dioxide. It's kind of a good proxy in general for indoor air quality. Carbon dioxide goes up, we get lethargic, and it kind of tells you if CO2 levels are getting high, you probably don't have enough fresh air coming into the home. I talked about PM 2.5. We also have to be concerned not only about the indoor air, but outside air as well. As you know, in the past few years, especially in the western half of the US, had a lot of wildfires. This year, it's a big issue in Canada. It's coming down. In California now, they require MERV 13 filtration on any fresh air. I think this is a trend that might, sweep across the country. Not only wildfires, but, especially if you live by a highway with a lot of traffic, a lot of PM 2.5 coming from, internal combustion engines. So we can't always assume outdoor air is going to be great fresh air.
So Patrick, just a quick question. Is that MERV 13 filter on the supply side? So from the outside air to the ERV, right? Right,
exactly. Whether it's the filter on an H or ERV, or if you just have a supply system, maybe just a supply fan, any form of mechanical ventilation, you want to have that incoming airstream have a good filter on it.
Great.
So what happens when we tighten the envelope? It's great for sensible loads, right? Helps us heat and cool our buildings, but it can be a problem with latent loads. You build a nice tight building, now all that shower humidity, all the cooking humidity, you're boiling water for pasta and so on, that has no place to go. So that's where we really have the concern. And, we're a good ventilation system, especially with recovery, can help us out. And one note there, depending where you live, you may have experienced in the spring and fall these kind of cool and clammy conditions. If it's mild enough outside temperature-wise that your AC doesn't run, but it's a high dew point, you really get those uncomfortable, cool, clammy conditions in a home. So it all relates. I want to talk a little bit about depressurizing buildings. As we're here talking about health, obviously radon is a big concern with health. I think number 2 cause of lung cancer. So as you see in the image here, one of the biggest concerns is the traditional style of hot water heater. As you can see at the top of this hot water heater, this is just naturally vented. It's not, there's no seal and a separate fan. You're just counting on the fact that those exhaust gases are hot and will rise up and out. But now you build a real tight building, turn on a big range hood, for instance, you could backdraft that carbon monoxide, again, radon. You have a depressurized building, radon's going to want to come in. So another thing we really want to be concerned about. If you're using an exhaust-only strategy in your home, when we open that door from the garage into the home, we don't want leftover exhaust gases from our cars and gasoline, anything else we have stored in the garage to come rushing in. So the next 3 slides here, just going to cover some ventilation basics. Obviously, we can't talk too much about ventilation, and we want to make sure everyone has a good footing for what we're talking about. If you're relatively new to the industry and you see some of these ventilation terms and wondering what they mean, I'll give you a quick 101 course here in a few slides. So HVI is the industry certification body, and it's the industry trade association. So if you ever get a few minutes, I highly recommend you go to hvi.org. They have out there a certified products directory. So you can go and you can filter by type of product, ERV, bath fan, range hood. You can filter by manufacturer, a lot of great filters. And you can see what the HVI certified, airflow, sound level, wattage. In the case of ERV, sensible recovery efficiency, you can see exactly what those certified levels are. You really want to look for products that are HVI certified. If they're not, you really just can't trust it. And more, the building codes are requiring HVI certification. In the case of, depending which version of the I codes your state or city is on, it's required that they be certified either for spot ventilation or in the latest code, even for whole house ventilation. So very important. I touch on zones a little bit. A lot of people say, what's a zone? I thought the rating for sound level was decibels. The concern with decibels is they're on a logarithmic scale. So a lot of consumers can't wrap their head around, logarithmic figures. So zones are on a linear scale. 2 zones is twice as loud as 1 zone. Want to point out, if you ever see less than 0.3, that's the quietest achievable rating you can get. ERVs are not rated for sound, but if you're looking at a bath fan or range hood and you see it has a rating of less than 0.3, that's the quietest you can get. They've determined at 0.1 and 0.2, the human ear can't even hear that. And in terms of a common question we get is, how loud is a zone? So 1 zone is about the equivalent to a quiet refrigerator running. If you're home alone and your refrigerator kicks on, you can hear it, but it's, most people aren't going to consider that objectionable. Well, on the other hand, 4 zones, that's your typical economy bath fan that most people would consider objectionable. I'll talk quickly about static pressure. This is very important when you're talking about ventilation, be it a bath fan, a range hood, or an HRVE ERV, supply fan, any type of mechanical ventilation. So static pressure is resistance to airflow as air is trying to move through a duct. So what we're looking at here, that red curve is called a fan curve. So you can see on the vertical axis is our static pressure measured in inches of water gauge, and on the horizontal axis is CFM. So as you can see, as a static pressure is lower, it's going to perform better. So if you follow that blue horizontal line across, that's at 0.1 inches, you'll see this fan moves 80 CFM. Unfortunately, so that's the standard rating point that HVI established decades ago. So when you see a rating point for most ventilation products, it's going to be at a 1/10 inch. So if you're buying an 80 CFM fan, it's going to be at a 1/10 inch. But it's becoming more and more important. If you look up at the 1/4 inch level there, that other black line, follow it to the fan curve and drop it down. This fan only moves 60 CFM at a 1/4 inch. A 1/4 inch is much more realistic static pressure. Most of the codes today, when they say how to check how much airflow you're getting out of a mechanical ventilation device, they say look at its 1/4 inch static pressure. In the case of a bath fan or hood. Of course, with the ERV, it gets a little more complicated. There you have 4 ducts and you kind of have to look at the combined static pressure of the system. But the point here is, make sure HVAC contractors are really paying attention to this. You look at the bullets on the left, one rigid ducting is better than flex. We don't want to minimize the duct diameter coming off the duct connector of the fan. If anything, increase it. Keep your duct run as short and straight as possible, and really think about quality termination fittings. You want them to be airflow friendly. So in most recent codes, ever since 2015, in the residential code, which majority of most states are on at least 2015 now, they give you 3 options to verify your airflow. One is probably the most common one is this allowable duct length table that we're showing here. So as I mentioned, the importance of 1/4 inch airflow. If you look in the upper left-hand corner of that table, you'll see the whole table is based on a fan's 1/4 inch rating. Again, we're talking about a fan or range hood here, bath fan or range hood. So as you look down that, let's look at the column that says flex duct, a 50 CFM fan, 50 being key because that's a requirement in a bathroom. So as you can see, a 3-inch diameter duct, if you look in that cell, there's an X there. That means it's not allowed. You're never going to move 50 CFM, in an economy fan with 3-inch ducting. You have to move up to at least 4-inch ducting. So more and more at the building codes, Washington and California have a similar table. But, duct length and duct sizes relative to fan performance is really becoming a bigger and bigger issue as they want to make sure, we're getting good ventilation in homes. The second way is to actually do a verification test. You see in the image on the right, this inspector, HERS rater, is actually measuring a bath fan. And then the third option is comply with manufacturer's design criteria. So the key here, again, the focus here in our webinar is good, healthy indoor air, no matter what type of ventilation system you put in, at the end of the day, you have to make sure it's performing and moving the airflow it's required. Touch real quickly, I'm sure you've all heard of 62.2, ASHRAE 62.2. This isn't a code, it's a ventilation standard. They update it every 3 years with addendums in between. For the most part, this gets referenced via the I codes, your IRC and IMC. There are a handful of states that in various ways reference it more directly in their codes, ones that don't use the I codes as directly. And it's a key element in a lot of above code programs and so on, like Energy Star, which is becoming more popular now with the 45L tax credit. So I won't hit all the bullets here, but the key pieces of ASHRAE 62.2, there's 2 of them. One, in terms of local or spot ventilation, in bathrooms, you need 50 CFM delivered at the end of the day. And in kitchens, you need 100 CFM, exhausted out of the kitchen. You need to have that capability once the product's all installed. Probably more importantly there, the major bullet at the bottom, dwelling unit ventilation. You'll hear it referred to as DUV. Other people call it whole house mechanical ventilation. So in the I codes, again, IRC and IMC, they still use the 2010 version of 62.2 because it's much simpler. In the 2013, 16, 19 versions, it's a much more complex calculation. So their intent is to keep it simple. So they'd rather have simplicity than people getting the wrong number because they miscalculated. So and again, that's used in some states, and then in weatherization programs, they use the newer versions. Real quickly, sidebar and touch on sound requirements. 62.2 says you should stay under 3 zones for local exhaust and under 1 zone for dwelling unit ventilation. These don't usually make their way into the actual I codes, but it is still good practice. If you're using whatever type of device, if the homeowner is going to turn it off because they find it objectionably loud, now they have no ventilation. So quiet operation really is a key consideration. I touched earlier on how we don't want to depressurize buildings. So I want to hit real quickly here, kitchen makeup air. As builders, I'm sure you've heard of this and have dealt with it. So in the IRC and IMC, in the simplest form, if your state doesn't make an amendment, it says if your range hood is 400 CFM or greater, you need makeup air. Now, different states and cities will adjust this. Some moved it to 300, some moved it to 600. Some say you have to make up all of it. Others say you only have to make up the amount over 400. So you should really check with your local code official on exactly what you need to do. But the idea here again is, let's run a low voltage wire from that range hood to a motorized damper like you see here in the image. When the range hood turns on, this damper opens up, just lets fresh air into the building, to balance that out so we're not depressurizing the building. So I mentioned earlier the most common form to calculate dwelling unit ventilation rates is the 22 version of 62.2. So again, ASHRAE is an engineering society. They do a lot of research. back in the day, they determined that the fresh air we need in a home is based on two factors. One is the total air volume in a home. Obviously, the more cubic feet of air you have in a home, the more stale air you need to get out, and fresh air to get in. And then the number of people. They looked at it that each person should have so much CFM. So the formula they came up with is 1% of square footage and then 7.5 CFM per person. To estimate the number of people in a home, they use number of bedrooms plus one. Figuring the master bedroom probably has 2 people in it, other bedrooms probably have 1. So a typical 3-bedroom home probably has 4 people. So as an example home here, a 2,500 square foot 3-bedroom home, 1% of 2,500 is 25 CFM for that half of the equation. And then 7.5 times 4 is another 30. You add those together and that home would require 55 CFM. If you don't like even that level of math, they also give you the table option, which you see on the right there, which of course it has to round up a little bit for each cell. But again, this is the most common way to determine how much fresh air you need. Real quickly, a lot of states, I should say a good number of states are either on 2021 I codes already or are looking at changing to them. So the new energy code has some very key changes. The leap from 2018 energy code to 2021 was a very significant leap. So, if you're in one of those states, you really pay attention to the differences. In the far northern climate zones, 7 and 8 ERVs are going to be required. But probably most importantly, for multi-family 4+ stories from the IMC, H and ERVs are going to be required in all but a few cases. Very small apartments or climate zone 3C, which is what Southern California, like San Diego area. So in nearly all cases, it's required in a prescriptive path. And even if you choose performance path, you're going to find that you're better off with the ERV. So very significant changes. So the 3 basic ways we can, 3 basic approaches to dwelling unit ventilation are what you see here: exhaust, supply, and balance. I'll cover them at a real high level here, and then I'll be turning it over to Travis, who will get into the nitty-gritty with balance, and specifically balance with recovery, which is really the way to go, especially for very tight energy efficient homes like EBA builders are building. So the first one is an exhaust strategy. Pretty simple. The idea here is let's continually pull stale air out, probably with a good, efficient, quiet bath fan running 24 hours a day. And then the idea is there's enough holes in the building envelope yet that fresh air will make its way in as we depressurize the building, with pulling bad air out. The advantage that some builders like is it's low first cost, low maintenance, no filters to worry about. But, do you necessarily want your building envelope to be your filter? Again, we're kind of focusing on healthy homes here, IAQ. That's where you want an ERV with a good filter. Again, it's the best approach, not only for efficiency, but health. There are a number of models of bath fans on the market that are kind of dual purpose. They'll run at that 55 CFM level that we talk about 24 hours a day. And then when you are in the shower, they'll kick up to a full 110 CFM capability and then fall back down. Some even have humidity sensing, will do that automatically. So that's the exhaust strategy. The kind of corollary to that is just the opposite as a supply approach. Here we're going to do just the opposite. Let's push fresh air mechanically into the home, and we're counting on some holes in the building envelope for the stale air to get pushed out. Good news here is we know where the fresh air is coming from, and we can filter it. We can even sense it. We can sense the outdoor temperature and humidity and maybe shut down in extreme outdoor conditions. There's 2 basic methods of doing supply ventilation. The first is what's called a CFIS system, central fan integrated. So here we're going to use the power of the central fan to pull fresh air in from the outside. So the image in the upper right there is a typical CFIS type system, just a motorized damper with a nice temperature and humidity sensing. And we're going to tie that in and let the central fan do the work. The other option in the lower right corner is a dedicated fan. This is really, if you're going to go with the supply solution, this is a better solution. One, it's more efficient. You know, these units, the ones you have pictured here, are happen to be Brown units, have a nice little DC fan, you know, using relatively very few watts. And two, you know, compared to a central fan using hundreds of watts to do a pretty simple job, and there's no heating and cooling call. But secondly, you really can control the airflow. You know, we've heard stories that with a CFAS system, when they check these out and verify them, they're not getting that 55, 60, in larger homes, even more than that. They're just not getting that airflow. So with a dedicated fan inside that housing, you can set it for 60, 75, 90, whatever you need, and you know you're going to get that. So you don't have to worry about you know, not passing at the 11th hour on your airflow verification. So exhaust and supply are kind of the two basic approaches. Depending what climate zone you're in, you may choose one or the other. But from here on, we're going to focus on balanced ventilation. This is really, you know, the key again is energy efficient builders like you are. You're building nice tight homes. The exhaust and supply approaches are counting on holes in a building envelope. If you're building tight, you don't have those holes. So you want to mechanically push bad air out, mechanically push fresh air in. So the most simple way to do balanced is kind of the image on the left here. You know, run a bath fan at 60 CFM, run a supply fan at 60 CFM. You're going to be balanced, which is great, but you won't get that great recovery benefit. You know, recovering the difference in temperature, the difference in humidity. So at this point, I'll turn it over to Travis. He's our expert in H and ERVs, and he'll kind of get into more how you might choose one or the other, how to install them, and so on. So take it away, Travis.
All right, thanks, Pat. Yeah, so as Pat mentioned, when we talk about balanced ventilation, we talk about that tight envelope. Kind of the next aspect of that is recovering that either that indoor air temperature that's coming in or the stale air that you're taking out of the building. There's two main types, and we'll talk through in more detail the HRVs, the ERVs, and how they can efficiently manage that temperature and that humidity, as well as how it can save on overall energy efficiency purposes. So we talk about introducing fresh air into a home, into that tight envelope we've done. A balanced ventilation system with recovery is the most energy efficient way to get there. So we are going to make that stale air we're taking out of the home do some work, and or have that fresh air we're bringing into the home do some work to temper that air that ultimately gets distributed to the house. So when we look at a balanced ventilation system, you know, what is inside this box? And so it starts with the filter. So if you really break down an H or ERV, it really comes down to three key components. The first of that is the filter. And so that's our first line of defense. So we, like Pat mentioned, we have a known source of fresh air. So we have a dedicated duct that runs to the outside, comes to a termination. We're going to draw that fresh air in through that duct. The first thing it's going to do is it's going to come across the filter. There's a number of different filter options. We'll talk through them, what that means. So again, that's our first line of defense that new, clean, fresh air has come to. We're going to have to bring the air into the home as well as take the stale air out of the home. And so that's done with blower fans. So inside this box, there are essentially two blower fans. One's pulling air in, one's taking the stale air out of the building and taking it back to the outside. This is where you can get into some more differentiation. So you can have, like Pat was mentioning, some DC motors or ECM motored blower fans, so higher efficiency, less watt usage. Again, let's make this product do some work in the most energy efficient manner. And finally, the recovery core. So for lack of a better term, this is where the magic happens. We'll kind of show you kind of what that means, what that looks like between the different models. But this is really where that tempering occurs of that outdoor air coming into the house and vice versa. So I talked about HRV, I talked about ERV, those acronyms. What does it mean? And so if I took that recovery core and I simply did like a cross section of it, what you're going to see is basically thousands of these little air channels, about 2 to 3 millimeters in size. And if I were to take a very microscopic look at the cross section of what's going on inside those, if we look at that upper right image, so let's say it's a colder day out here, we're bringing that cold outdoor air into the house. into our ERV. We're taking our warmer air from inside that we're drawing from that dwelling, that stale air that has those pollutants that Pat talked about earlier. And what we're going to do is we're going to have an exchange. So very simple, hot goes to cold, wet goes to dry. So if we have cold air coming in and we got warmer, hot air going out, we're going to go ahead and that hot air is going to make its way to that cold air. And what we're going to do is we're going to deliver a tempered, fresh supply air to that dwelling. So just like that image shows there, that exchange occurs between each of those very fine layers within that membrane of that core. So, and the two air streams do not touch one another. They're simply passing, in this case, perpendicular to one another, and that exchange occurs between each of those layers within that core material itself. So when we talk about this exchange, the first is a heat recovery ventilator, or HRV. An HRV simply does a sensible transfer. So we're simply dealing with temperature. What's the temperature of the incoming air? What's the temperature of the air that's going out? What am I going to expect for that tempered air to enter after it goes through the HRV? An ERV, or energy recovery ventilator, has both that sensible piece as well as a latent transfer, moisture vapor. So we have added an additional component. Not only are we going to get the benefits of a sensible transfer, making that outdoor air and our indoor air work with one another, we're also going to get a moisture vapor piece. So that exchange that would occur, again, wet goes to dry. So if we have humid air entering the house from the outside, and we've conditioned the indoor air, whether it's through dehumidification, air conditioning, basically how we've dried some of that house air out. Again, that moisture is going to basically make its way back to the outside, some amount of it, and we're going to deliver a little bit lower humidity air from the outside when it passes through an ERV. So we talk high level, HRV, ERV. This is what's going to fundamentally be happening, and that's what's going on inside of this recovery core. As simple as the nature, like I said, it's the most energy efficient way to temper that air, that outdoor air that's coming into the house, just simply by passing through this recovery core. I'll give you some examples here shortly, showing some real world examples of what that looks like, depending on the efficiency of that recovery core. So often get asked, if we look at this climate zone map, you guys are probably more than familiar with it. You talked about HRVs, you talked about ERVs. I'm located in, let's say you're located in Chicago, Illinois. So we're in climate zone 5. We're on the moisture side of it. So we're in 5A. What is the best solution for me? If you asked that question maybe even 5 years ago, I would certainly still probably be hedging towards an HRV. The thing that has changed over the last probably 5 to 10 years is our ability to deal with moisture inside an ERV core in those colder climates. So like a Chicago, Illinois, or Minneapolis, Minnesota, or Milwaukee, Wisconsin, where we're located near. Our ability to keep that core from turning into an ice cube. So if you can imagine that ERV, we talked about that moisture vapor, or that latent component, we're going to be retaining some amount of moisture. And so when we bring that extremely cold air in from the outside, the last thing we want to do is to have that core begin freezing. And so, as it freezes, it'll continue to expand. We're going to start deforming those very small air channels that we talked about previously. So between the materials in which we make that recovery core out of, as well as our ability to defrost that core efficiently in a very timely fashion, has really taken that line of where an ERV can be sustainable or used throughout the year has gone up. So probably back 5-ish years ago, I would have told you climate zone 4 and below ERVs. I can confidently say climate zone 6 and below for sure. We're not quite to the polar bears yet, but we're getting closer to those polar bears in climate zone 7 and 8. But I personally have an ERV in my house. Like I said, I'm located just outside Milwaukee, Wisconsin. We had a stretch there this last winter around Christmas time. It didn't get above -10 degrees Fahrenheit. And I just let my ERV run continuously during that time. And again, it's effectively managing that moisture through that defrost cycle, through the materials in which that core is made out of. And we'll talk a little bit about other advantages to an ERV in those different climate zones. Even if you're in a drier climate zone, like a 5B or a 3B, you still have advantages when it comes to an ERV that you have over an HRV. All good with the chat so far, Aaron? Any questions?
Yeah, all good. Just a reminder, you
Okay.
can put questions in the Q&A section and we'll get to those, but nothing else thus far, Travis. Thank you.
Perfect. All right, so let's talk about the temperature management of this. So let's give a cooling season. So we talked about that recovery core earlier. It has a certain amount of efficiency. So how well is it going to transfer, in this case, that temperature from one to the other? So I didn't go to school real long, so I'm gonna give a very simple example as a start. So let's say it's 0 degrees outside and you heat your home to 100 degrees. If I have a 75% efficient recovery core, I'm going to take my 0 degree air that is in the outside, and it's going to be tempered to 75 degrees once it passes through that core and that core has stabilized. So it is that delta or that temperature difference between the outside and that inside air that we care about. And whatever that delta is what we take a percentage of to predict what the incoming air, in this case, that pre-treated air to the house will be. So as you can imagine, as those deltas become larger and or the efficiency of that core becomes better, we're going to be able to take that outdoor air and temper it to a more a closer temperature to what that indoor air is. So as an example here, this is simply just temperature. We have an outdoor condition of 110 degrees Fahrenheit. We've cooled our air in our house to 75 degrees. Those two air streams that we talked about earlier, how they're passing through that recovery core, based on the efficiency of this recovery core, we can expect that what would be 110 degree air, outdoor air coming into our home, we've now filtered it. We're now going to temper it, and we're going to deliver, in this case, 83 degree Fahrenheit tempered air to the house, whether it's directly to the home or to the air handler. Again, we're going to let that indoor air, that bad indoor air that we talked about, that Pat mentioned about all those different pollutants, we're going to make that do some work. And so by going through that recovery core, we're going to pre-treat that air entering their home. The same could be said to the heating conditions. So again, this is where, as those temperature differences grow more and more, so it is negative 13 degrees Fahrenheit. I'm heating my home to 75 degrees. My wife likes it nice and warm. I'm taking that negative 13 degree Fahrenheit air and conditioning it all the way up to 61 degrees Fahrenheit in this given situation. So again, we're making that bad polluted air pulling from the home do some work to treat that air that's coming into the inside. And again, throughout this process, we're passing it through a filter at the beginning. So we're going to have a source of fresh, filtered, tempered air passing into our home, ultimately diluting our indoor air with fresh filtered air, as well as pulling that stale polluted air out of the house. Similar to temperature, humid. So humid climate. So we've got a higher dew point outside. We've either used a dehumidifier or air conditionings do a nice job of maintaining our relative humidity and dew point inside. We're gonna wet goes to dry. So we've got wet air, humid air coming in to the in this case, the ERV, and we're gonna take that drier air from the inside. We're gonna pass it across that core. And so that moisture vapor is going to exchange like we showed earlier. And we're gonna take some of that humidity back to the outside. I cannot repeat enough, an ERV is not a dehumidifier. It is not a dehumidifier, but it's certainly going to reduce what would be just raw humid air coming in from the outside in those hot, humid climates. So again, we're going to take some amount of moisture out of that incoming air and deliver that pre-treated air to the home in those humider climates. The opposite could be said too. So in a drier climate, think of, Phoenix, Arizona, again, that 5B type climate area where it's very dry outside. A personal story I'll share quickly. I had a humidifier in my home. So during the wintertime in Wisconsin, I had a newer home. I'm worried about my wood floors getting too dry in the winter. So I added a whole home humidifier to my house. The thing I noticed, because I'm a geek and I was measuring my air prior to even starting at Brown, understanding what my relative humidity looked like throughout that season, I could pretty easily predict when my humidifier turned on, because my relative humidity inside my home would ramp up to that 50-55% I was looking for, and then would drop off quickly after my humidifier turned off. something I've noticed over the last year and a half, 2 years now that I've had my ERV in, so I got about two winters under my belt. My relative humidity has stayed very consistent throughout those winter months. And it's because I've added humidity through my humidifier in my home. I'm in a dry season with our winters here in Wisconsin, but my ERV is effectively capturing some of that moisture I'm introducing to my home. So the days of seeing that roller coaster, my relative humidity inside my home, fluctuate greatly, has basically flatlined. And so an ERV, because of its moisture exchange that's also occurring, can be beneficial in those drier climates because of that additional moisture retention I'm getting. So if you are in those types of climates and you are adding some type of humidity, whether it's through a humidifier or some other source, and you're looking to maintain that humidity, an ERV is a good option to be looking at because of exactly what's being shown here. And again, I'll share that personal experience that I had, an experience over the last year and a half or 2 years I've had an ERV in my house. So those are kind of the breakdowns in the real world, what it can look like. And again, these can vary depending on what your efficiency of your core is, what airflow is going into the system, but it just gives you a general idea how it is, those different components that we talked about earlier, how they're effectively delivering, in this case, fresh, filtered, pre-treated air to the home to ultimately ventilate it properly. Pat showed those pictures earlier. I'm going to share them again, just kind of what's going on from the outside. So you're asking, hey, you're bringing fresh air in. What are you doing about it, before it gets into my house? And so there's a number of levels when it comes to filtration, starting with PPI. Basically, it's just catching the big stuff, bugs, anything that could make its way past possibly the inlet filter or the inlet perforation. Then we step up to MERV 8. So we're kind of walking through the different levels here. MERV 8 is kind of the next standard, I will say, in terms of the filtration level that you may find in some of these different ventilation products. So you're going to see these little infographs. If you go to your local hardware store in the furnace or the air handler filter section, you see very familiar infographics here. What is it it's capturing? As Pat mentioned earlier, when we talk about that particle matter, we're talking about that size. And so why MERV 13 as an example, and like Pat hit on, is that particle matter size. So why is it effectively capturing it? It's because in the case of the pandemic, or what COVID kind of brought a light to, is MERV 13 became a hot word because the particle matter size in which, in this case, the virus could attach itself to, could be captured efficiently with the MERV 13 filter. So that's why you see states like California, or even local cities like Burbank, California, as an example, because of the high traffic area, mandating MERV 13 as a supply filters because of that particle matter, how effective it is at capturing that. And then when you jump up to HEPA, HEPA is capturing that particle matter. It's just doing it much more efficiently. The medium which it's made out of, it's just doing it more efficiently in capturing that particle matter at a much finer rate. So again, as you step up in filtration, again, in which you can do to capture that incoming particle matter, or whatever it might be, from your outdoor air source. Again, just think about filtration levels, understand what it is you're trying to accomplish when it comes to filters, and know that many of the ventilation solutions, including what Broan offers, has the ability to upgrade from MERV 8 to a MERV 13 or even up to a HEPA. So,
Travis, is there a crossover between MERV ratings, which I think us in the industry are more familiar with, and the HEPA rating, or am I specifically looking for a HEPA filter?
Yeah, so MERV 15/16, Aaron, would be the closest to the HEPA. From if I were trying to do apples to apples, there are some differences in the media material in which HEPA are made out of, so that they're, I'll say, less restrictive when it comes to versus a MERV type filter. So there's different targets there, but I would say between a MERV 15 and 16 is where you're going to get the same capture rate as you would with the HEPA. HEPA is just more of a name. We have HEPA filters in our vacuums, among other things. HEPA is kind of a key word that consumers have latched onto versus many of us in the industry understand MERV. So
yeah, I think that's what we found from some research that we had presented last week, is that the consumers get HEPA, the builders and HVAC people get MERV, but if you're going for a healthier home, you probably want to advertise HEPA so your client understands it.
Exactly. Like you said, it's kind of a hotter word. Like you said, people have filters in their vacuums or even these HEPA air cleaners now. HEPA is just something that's out there versus many of our, us talk about MERV, which goes on deaf ears when it comes to consumer. So
great. Thank you.
Yeah, absolutely. All right, so we got about 15 minutes here yet. We'll talk through installation quick when it comes to HRVs, ERVs. I'll just give some real world examples. Again, there's a lot of variables that come into this, but I just want to touch on the 3 key ways that they can be installed and considerations to be keep on top of mind when we talk about that. So the first is, just like the name states, simplified. So this is where we're going to utilize the existing home's ductwork to distribute the fresh air and take the stale air out through the H or ERV. So again, in all these cases, we need to be drawing fresh air in from the outside, taking that stale air out from the H or ERV to the outside. So you're always going to have 2 ducts going to the outside, but how we distribute it to the house is going to vary. And so in this case, we have the simplified method. So the picture I show here, in this case, we're going to the return side of the air handling system. We do want some separation of those 2, as well as this will require that the central fan of the air handler be running. Otherwise, in this case, we just create this loop in our H or ERV, would just be recycling air inside that return duct. So there is some interaction that's required here between the air handler fan and the H or ERV. There's an alternative to this. Instead of taking that fresh air and putting it in the return side, you can put it in the supply side. There's some other things to be mindful of when you do that. You should have interaction with the air handler yet, because you are distributing, in the case, let's say it's a very cooling heavy time of the year. So our air conditioning, particularly for using sheet metal ductwork, could be very cold. And even though that the H or ERV is doing a good job of tempering that air, it's still becoming, we could still be pushing, in this case, warmer air onto a very cold surface, and we may have some concerns about condensation on that ductwork material. So again, this is, like I said, the name states simplified. It's typically the least costly because we're utilizing ductwork that's already in the home. And again, we're going to utilize that distribution system to direct that fresh air throughout the house in that return ductwork. The next is a dedicated exhaust. So we're not overly sophisticated. We name them pretty straightforward. So we have a dedicated exhaust or exhaust ductwork that runs to different areas of the home, typically like the bathroom or the kitchen, the laundry room, those very high polluted areas. We're going to want a key drawing source to remove that stale polluted air from those areas of the home. And so just like that image shows on the left, where we have dedicated ductwork that runs those areas of the home, we're still going to take that fresh air from the outside, pass it through that H or ERV, and we can either put it in the return side or we can put it in the supply side. And so, again, this is kind of the next step. We have seen this used very often to be used as bath fans, be able to replace a bath fan with an extraction point of an ERV. In the case like I show there, you can see that lower left picture there, they just have a simple grill being in the bathroom itself, and then they just have an override switch that you'd push to boost that H or ERV into high speed. If it's running continuously, let's say at that 55 CFM example that Pat gave earlier, and then let's say the unit's capable of doing 160 CFM, you do have the ability to hit that boost speed switch. It'll go, depending on how much you hit it, it could boost that ERV or HRV up to that 160 CFM for a certain period of time, and it quickly extract that stale air out of that bathroom. So again, something that's used quite often, particularly this was used quite often in Canadian markets because sometimes they do use like baseboard heat instead of having a ducted system. So this is another way to get there. A lot of multifamily applications are going this way, again, due to simplifying the needs for terminations in the outside, as well as just overall ductwork itself.
Travis, are you seeing this with air source heat pump deployment as well, where, if you have a mini split system that you've gone to in your house, you still want to have that fresh air delivery throughout the whole home? Then is it best to go to dedicated exhaust installation?
So that would actually, Aaron, so if you don't have, so yeah, so if you don't have, if you don't have any ductwork at all, let's say you're just, using mini split heads, that's where you go to a fully ducted system. And so that's where we're not relying on anything. We have run our own ductwork in these types of applications. And just like you said, we're particularly seeing this very common when you talk about, utilizing those mini split heads throughout a dwelling. And in multifamily applications as well, where they may be using other ways rather than having, a distributed HVAC system, they are using those mini split heads or whatever it might be. That's where you would go to a fully ducted system. A real world example there shown on the bottom right. This is an ERV mounted actually into a ceiling assembly, and then they ran ducts just like that floor plan shows above that. They ran dedicated ductwork to those given areas of, in this case, a smaller apartment complex dwelling. So again, different ways you can get there. And again, it really, there's a number of variables that come into it. But kind of once you've done a few, you get a few under your belt, you kind of understand, it becomes pretty straightforward. Again, depending on what floor plan comes across or what designs, you can kind of piece it together from there, knowing that you have different ways to get there. So that kind of provides, again, high level, the different install methods, kind of the ductwork routings. Again, things can get a lot more complicated, but just know that there's different ways to get there in different product platforms, depending on where you have the ability to install, how you have the ability to duct it. There are a multitude of different models that are out there to do so. Something else, again, to be considering, we talked about, you always need to be bringing fresh air in, pushing stale air out through an H or ERV. There are different exterior terminations. You can use your standard caps like you saw, or your roof cap in the case of a stale air, like you would have, but there also know that there are tandem or concentric type terminations where you can bring and fresh air in as well as take that stale air out in a single penetration. These are taking off like hotcakes, particularly in multifamily applications. So architects, designers, the last thing they want is any more terminations on the exterior of the building. But again, they need fresh air ventilation. They need HRVs. These tandem terminations or these concentric terminations have become very popular because of that. And again, we as manufacturer, among others, do validation to validate that the contamination rate, so how much of the stale air we're putting out of the H or ERV gets drawn back in. So from a design standpoint, from a airflow standpoint, obviously we're very conscious of that and making sure we stay well below the thresholds that ASHRAE in particular has set for different applications. So just know that they're out there. You're not always confined to having to put a separate termination in two different areas. You do have the ability to use these tandem terminations as well. All right, so Pat talked about kind of the different ways to ventilate, the different pollutants to be considering. We're going to talk about what the future looks like. And so we talk about automation. We talk about monitoring in real time what it is that's going on inside the house. So I'll use the example, you're having a group of friends over, everybody's hanging out in the kitchen, bottle of wine are getting opened, everybody's chit chatting, there's a lot of CO2 and there's a lot of hot air in the room going on. It's that time that, we want our ventilation systems to function properly without any intervention. So the likelihood, if I got a party of, friends over, the likelihood I'm going to be thinking actively, hey, I should turn my kitchen range hood on because we're all hanging out in the kitchen, is far and few between. So let monitoring systems manage those for us. Let them talk to one another. So we are building out systems that are interacting with different ventilation pieces of equipment. So whether it's that kitchen range hood or the exhaust fan or our fresh air systems, they all can intertwine with one another. So as an example, if your kid takes that 20-minute, 30-minute shower that they're used to and they don't turn the bathroom fan, you got excess humidity, let's have that bathroom fan turn on and regulate as it's necessary. And so we're not just worried about simply odors or humidity, we're also picking up things like VOC, PM 2.5. So there's a number of other particulate matter or pollutants that we're able to monitor throughout the home to actively manage the ventilation properly. And so that's where the future is. It's already here. We're also seeing connection between what's going on outdoors and how we can interact with the indoors. So Pat gave those examples of the wildfires. We had wildfire situation here even in Wisconsin from Canadian wildfires. I don't want in this case, at that time of the day, I don't want my fresh air system bringing that wildfire air in. So let's have these systems interact with what's going on the outside. So what does our outdoor air quality look like? And is it a time to be bringing fresh air in or not? And so that's really where we're going to be, is we're going to be connecting what's going on inside the home as well as what's going on to the outside, in making those decisions properly to always optimize your indoor air quality. And so that's where this automation piece comes in, and the devices and the ventilation all intertwining. And you can give it, that management directly to the homeowner if they so choose. They can decide what are the thresholds in which they want to set for their different areas of their home. And that's all done through a phone-based app. And so that's really kind of where the future is. And like I said, we're there in most cases. The industry is building out different monitoring systems. Again, what Pat mentioned earlier about ASHRAE and others have recognized the need for more on-demand ventilation. That's where these types of systems are coming. So it may not always be that, ASHRAE 62.2 says we need a continuous CFM at 55 CFM. Let's make better decisions based on what's really going on inside the home, or vice versa. What's going on the outside? Do I really want fresh air during this time of the day, if wildfires, whatever it might be? So this is really the future, is this smart dwelling unit ventilation. And there's a number of pieces of hardware that are being built out to fully sync what's going on both inside the home as well as outside the home. And so that's where we see the future going. And like I said, in most cases, we're already there. It's only going to become better over time. So I think with that, and thank you guys for your
Travis,
time.
Are we seeing 62.2 change to accommodate that type of system? Can you just speak a little bit to that?
Yes, ASHRAE 62.2, gentleman Max Sherman is kind of heading up the effort to add another alternate compliance path. Instead of, again, just running 55 CFM continuously, let's sense all these different things and, allow builders to do it a little differently, to do it more efficiently, not hold their feet to the fire. I want 55 CFM 24 hours a day. As long as you're doing it in a way that's going to provide good indoor air quality, if you can do it more efficiently, they're going to have an alternate compliance path. Hopefully that'll be ready in the next version of 62.2, but it's being worked on.
Fantastic. And can you talk about, we've got builders that are doing Indoor Air Plus, Zero Energy Ready Home program with the new Inflation Reduction Act rebates. What's the ultimate specification for delivering the healthiest home? Or is there a resource at Brown Newtone that we can bring our plans to, and they can help us make sure we're speccing to the latest, greatest technology?
I think I think the latest, greatest, when you look at the latest version of the energy codes, and Travis can jump in here, I think it's all about ERVs and the efficiency of the ERVs and what's the SRE level. States like Washington, for instance, they not only want you to put in the ERV, but you get extra credit points if you put in an ERV with the SRE level of 75 or 85 and so on. So, I think the Holy Grail is going to be one, to do it smartly, sense all these different things. Different cities or states have different utility rates at different times of the day. Let's ventilate more in the middle of the night when, the coal plants aren't running, to run everyone's air conditioners during the afternoon. But again, just getting things like ERVs to be as efficient as possible. Again, states and cities are starting to award kind of energy bonus points for that.
Yeah, and it's always tightly correlated to the building type piece. So the air changes per hour, how tight your envelope is, Aaron, is more times than not tied directly to how you're going to ventilate it. So like Pat mentioned that Washington example, based on the building tightness, how quickly or how efficient am I building my tight envelope, but also ventilating it? So yeah, I think that from a holy grail standpoint is those two combined. So
Great. And I think what we're seeing here is the Overture product.
Yep.
Can you talk about, because it's not just, if I'm understanding it correctly, it's not just for a new home project. It's something that could be added and run systems in the house. Am I right in how I read that?
Yeah, so there's kind of a few different pieces of hardware there. It was kind of initially sent out so that the product physically in the center there is a plug-in sensor. And so it monitors PM 2.5, TVOC, humidity, temperature. So that is a plug-in version, so like a retrofit type application. The other pieces of hardware, like the smart switch that's kind of off on the right there, can take the place of an existing wall switch. And so the system was designed initially from a more of a retrofit type standpoint because exactly we have a large install base. And now we're introducing, I'll call it more permanent, like a hardwire type wall sensor that is more, fits more into just a flush, nice, clean look. And then the smart plug on the left there, that's what your fresh air system device would plug into, like your ERV or your supply fan we talked about earlier. So those pieces of hardware, like I said, are designed for both a retrofit application as well as moving forward a more seamless hardwire type application with like that room sensor. So yeah, we're continuing to evolve.
So Travis, could you take that plug on the left, put that in line with an existing vent hood in a kitchen, and it would turn on and off depending on air quality in that kitchen?
So like in a kitchen range application, Aaron, you would actually use that smart plug, a smart switch on the right. It has some monitoring capability. So it would take the place of, if you have a switch for your kitchen range hood, you could do it there. And so, yeah, there's different ways in which, depending on what equipment you have, that we can pull together what it is that you need based on what it is that you're looking to accomplish.
Fantastic. And is there anything that we need additionally on the outside of the house to monitor outside temperature, or is that done through the app? And
yeah, so it's all done through the app. So we utilize a network of outdoor air quality services. And so based on your location, your zip code, depending on how hyper local the weather station data can be, we're utilizing that, basically that cloud of data to make those decisions. So there's no additional hardware that's required. It's all built in through the app and then ultimately, pushed to those different devices. So as an example, if the outdoor air quality has reached a threshold that we've determined is not good, it will have the ability, if you have that smart plug for your H or ERV or supply fan, it'll have the ability to deactivate that product for whatever given period of time in which that outdoor air quality is deemed too bad to be bringing in fresh air from the outside. So.
Fantastic. Talk to me about the new, I think it's the AI series. And is that what we're talking about when we say everything is built in and it's ready to go and it's smart, and or is it any of the offerings from Brown-Newton?
Yeah, so the AI series product line of HRVs, ERVs, we kind of took a few steps with it in terms of, we talked about those different insulation types, and a lot of, particularly I'll talk for the US, these particular products are quote unquote newer to the US. And one of the biggest pain points for installing contractors, builders, such and so forth, was the installation process and making sure it's operating properly. So like what Pat had shown earlier about, the validation of airflow, you can put this device in, if it's not providing the right airflow, you've defeated the purpose. And so the AI takes that variability out of it, in that it is truly, everything is built into the product from an airflow verification standpoint. So installer does their job. First time you plug the unit in, it's going to go through basically diagnostic of the install, tell you I can comfortably deliver X CFM with this install type. If that's good, then you can dial your CFM into whatever that number you need is. And then as things change over time, the artificial intelligence piece or the AI piece is it continues to learn. So if I set my target CFM, let's say to 55 CFM, and my filter becomes clogged for whatever reason over periods of time, the AI product is going to continue to compensate to always hit that target CFM that we set at 55. So it will change motor speeds. It could be changing different things within the product, damper positions, to always hit that target CFM, regardless of what's going on anything it can't control. So filters getting clogged up, terminations getting clogged up, whatever it might be, it's going to try to continue to always compensate to overcome those types of things. So that's really, so we took care of the install piece by making it as simple as possible. And then we're taking care of over the life of the product, making sure it maintains that CFM, maintains the ventilation performance that we're expecting over the life of the product. So that's really what all encompasses from the AI series standpoint. And we're continuing to build that into other products throughout our product lineup at Broan.
That's fantastic. It's just the kind of innovation that we've come to expect from Broan NuTone. I know you're going to be presenting at the EBA Summit, October 10th through 12th in Salt Lake City, and you'll have a booth there. Great opportunity to learn more about these great new products. And then people can reach out to Travis or Pat as well. And we will upload this video in the EBA Academy, and it'll also be at the Better Homes, Better Future podcast coming soon. So Travis and Pat, thank you as always. I know I've heard it before, but it's always a great reminder. And I think the technology is changing so quickly that it's a fantastic update. Thank you, gentlemen.
Thank you.
Yeah, thank you.
Thank you, everyone. Goodbye.